Hello, so today let's continue on with implementing our Game Boy emulator. Uh, Still using Claude code. I have already set it up to gain some context. Now, I think the next thing that we should implement, so we're done with the CPU, is probably loading up cartridges. So I think the next thing is to be able to take a Game Boy cartridge file, like a ROM file, and then load it up into memory at the appropriate address space. So taking a look at cartridges here, at least let's take a look at the memory map. And I'm learning on the fly. Um, I think most of the stuff that is going to be loaded from the ROM is going to be from 0000 to 7FFF. Um, and then I think the RAM that is going to be allocated for the cartridge is in this address space. What we're going to do before we actually start making these assumptions is since we're using Claude, I would like to get a second opinion on whether or not I have this correct assumption. So let's do this. Let's start giving it details on that of our intention in wanting to implement ROM loading, or at least cartridge loading into the emulator. Let's now move on to supporting cartridge ROM loading into memory for our emulator. This is the next step, I believe. It should allow us to have our CPU start running some code. Before we do that, let me give you my thoughts. Okay. We first of all, I think we should abstract the concept of a loaded ROM as a cartridge class. Cartridge class should contain very minimal API to operate on a cartridge or store to store, get to store and get data, right? Store and get cartridge bytes. I guess ROM bytes. It should also contain, and now if you think about it, looking at the specs of the cartridge, if we take a look at, let's see, the cartridge, they all have headers, right? So we should also be able to parse the headers and store them as instance variables like manufacturer code, CGB flag, all these things, right? So we should at least be able to create variables that will store this information inside the cartridge. So yeah, let's take that into consideration. Most likely necessary instance variables that contain the header information. Okay. Two, we need to figure out how to tie in the cartridge data into memory, RAM, right? The Game Boy RAM, because the Game Boy RAM is memory mapped I/O. So, can you confirm with me that the address space for loading a ROM is within 000 to 7FFF? Please correct me, teach me. And then three, let's see, where is cartridge RAM located at? Is it, let's see here, is it from A000 A000 to BFFF. Yeah, let's do that. Let's say, is it from A000 to BFFF? Ideally, before you do anything, please always try to confirm with me, and additionally teach me as I am learning about Game Boy emulator development as I am going along. So please, so I would like to emphasize, I like to emphasize that you also tell me information as if you were teaching me about the Game Boy hardware. Okay, let's see what it comes up with. So I think the easiest thing to do is just like a cartridge class where we just have like a dot read to read in some ROM. And when that happens, we can just kind of scan the cartridge for parsing out the headers and just storing them into specific instance variables. The challenge here is to, okay, well, now we have the cartridge class. How are we going to connect that with our CPU and memory that we have right now, so that basically, gracefully, if we were to tap into a specific memory address in RAM, how do we route that to specific cartridge data? So, okay, here we go. Great questions. Let me walk you through how the Game Boy memory map works with cartridges. So the Game Boy memory map, we have, remember, for the Game Boy, we have 64 kilobytes of address space going from 0000 to FFFF. And these are the regions that are supported, where like each region memory is given like a purpose for memory. So from this range here, it's for ROM. Okay, so that's the cartridge stuff most likely. And then from here to here, from 8000 to 9FFF is video RAM, so VRAM, 8 kilobytes worth. And then we have cartridge RAM. So that's basically, so funnily enough, all cartridges in Game Boy have their own RAM inside. So if you think about it, a cartridge, a game cartridge is kind of like an expansion peripheral for a computer. You can think of it as like a PCI card, right, or a PCIe device. And so not only do you have the ROM in the cartridge, but you also have RAM. And how do you actually tap into that RAM in the cartridge? Well, it gets mapped into these addresses, right? So these addresses in memory kind of reroute back to the RAM inside the cartridge. You also have the work RAM, which is the 8 kilobytes worth for the console itself, the Game Boy. And then you also have a mirror of that. And then you have sprite. We call it, sprite attribute table, but it's basically data and how you can actually render out sprites. Then you also have some unusable memory, and then you have I/O registers, and then you have high RAM and the interrupt stuff. Okay, so my question is: ROM loaded at 0x000 to 0x7FFF? Yes, but with nuance. The first 32 kilobytes of address space is cartridge ROM. Wait, I just said that. I just asked that. Okay. 0x0000 to 0x3FFF is bank 0. The first 16 kilobytes of the ROM file always visible. Okay. This is always visible. This contains the cartridge header. So from this address to this address, that's the cartridge header, the entry point, the Nintendo logo, and startup code. Cool. So this first bank 0. Now, from 4000 to 7FFF, it's a switchable bank. For small ROMs, which is our 32 kilobytes or less, like simple games, this is just the second 16 kilobytes mapped directly. For larger ROMs, like Pokemon at about 1 megabyte, this window is bank switched, and the game writes to special registers to swap which 16 kilobyte chunks appears here. So let's assume that then this is always staying like put, right? Once you load up cartridge data, that data that is corresponding to bank 0 is like there all the time. Now, if your game is bigger than 32 kilobytes, for example, that this second bank here is going to be used for like a 16 kilobyte window of code. And there is a register that you can write to actually swap specific banks to run different code. So think of it, you make a function call that's in another bank, for example, or another window of 16 kilobytes, and that this bank is going to get switched to that window of code that has that function call. So yes. So is cartridge RAM at 0xA000 to 0xBFFF? Yes, exactly. This 8 kilobyte window is external RAM that physically lives on the cartridge PCB. It is not part of the Game Boy console. Not all cartridges have it. Pokemon Red, Blue do. This is where your save file lives. It's battery backed SRAM, so it persists where it's powered off. Okay. So it's, again, like what we just said, right? It's RAM that is inside the cartridge, not inside the console, but we route the memory addresses to that cartridge. And usually it's used for save files. Okay, cool. Probably more because 8 kilobytes is quite a bit for Game Boy. So probably more than just save files. For cartridges with more than 8 kilobyte of external RAM, this window is also bank switched similar to ROM banks. So memory bank controllers, MBCs, this is where it gets interesting. The Game Boy itself has no bank switching hardware. Instead, the cartridge contains a chip called an MBC, okay, memory bank controller. The cartridge header at 0x0147 tells you which MBC the game uses. So if the value inside this address is 0x00, that means there is really no bank switching. It's just pure ROM. 0x01 to 0x03. Any of these values indicate MBC1, which is early games. Then you have 0x05, 0x06, MBC2, some games, 0x0F to 0x13, MBC3, which is Pokemon Red Blue. So let's take a look, let's keep a lookout for one of these values inside 0x0147 to help us indicate what memory bank controller we want to use. So Pokemon Red uses MBC3 with battery backed RAM, cartridge type 0x13. This means we'll eventually need MBC3 support, but we can start with ROM only and basic bank switching. So the cartridge header, okay, so this is what I was talking about, right? Like every cartridge has specific metadata associated with them in order to do stuff, right? Like where do I begin, right? What address do I begin to run the game? Where's the Nintendo logo? The game title, and this is just ASCII characters, about 16 letters long. Whether or not is a Game Boy Color game. What kind of bank switching you doing? ROM size code, RAM size code, and then the destination. So are they a Japanese game, non-Japanese game, and then checksum. So checksum is basically assuring all this information is what it's intended. Okay, so yeah, so Quad Code says, I agree with your instinct on the cartridge class. Here's what I'd suggest for the first pass. Cartridge class loads a GB ROM file, parses the header, exposes raw ROM bytes. Then wire into memory, reads from 0x000 to 0x7FFF, come from the cartridge ROM data, reads from 0xA000 to 0xBFFF, come from the cartridge RAM if present. Start with ROM only. Type 0x00, no bank switching, just map the first 32 kilobytes directly. This lets us validate the pipeline before adding MBC complexity. Yes, let's just do this a step at a time. I think first a cartridge class that can open up a ROM file, and perhaps, okay, open up ROM file and just stores separately header information. Okay, multiple instance variables and the raw ROM data. Let's talk about how the cartridge class can integrate with memory afterwards. Okay, so yeah, I really only want to right now have it implement the cartridge class so that we can actually understand how we're going to tie that in with our GB memory. So just like for review here, GB memory is a representation of, see, it's a representation of RAM, right? So this is an abstraction, or what do we call it, of RAM. And it's an instance variable. I think currently in our design, I think GB CPU takes an instance of that directly. And so most likely cartridge class has to do the same, but it has to be like the same instance, right? Oh man, we have a lot of imports here. Okay, so let's see here. Maybe not. What is interrupts? Wow, we need to start making things smaller. Okay, so yeah, here. So memory, right? It takes in memory. So we're gonna have to also receive the same memory instance. And so you have basically, if you think about it here, let me just open up Excalidraw. Uh, Excalidraw. Okay, so you think about it here, you have like the CPU, right? So CPU, and then maybe you're gonna have the cartridge, okay? The cartridge, so ROM. And so then you also have, in this case, memory. And both of them actually receive the memory. So they're sharing the same instance, and that allows them to like read and write into the same address space in this case. Let's see, I should probably change this to dark mode. There we go. Just make it like this. Yeah. So, yep. Okay, so yeah, that's pretty much what we want to do. Um, all right, so now let's go back and see what Claude said. Claude says, "Okay, where should the cartridge class live? I'm thinking a new source cartridge directory matching source CPU, source memory pattern with a GB cartridge file. Sound right? Yeah, why not? Simple enough. So I expect this implementation to be pretty simple for now. Hopefully it keeps it simple. In the meantime, let's grab uh, like a Tetris ROM. What's it? Simplest Game Boy game. What is the simplest Game Boy game? Like actually Game Boy games by release date. I think that is like a good like indicator of if something is simple or not. Let's see dark mode. Okay. Uh so we ordered this by date. Oh geez. How do we do this? North America? Okay. When did the Game Boy come out? Nin- yeah, when did the Game Boy come out? I actually don't even know. 1989. So it should. Why is it like 1992? Like that's so late. Let's see. List of games. Okay, list of Game Boy games for the original Game Boy. It should be kind of odd, right? Weird. I don't think Wikipedia is a good source then. List of Game Boy games by what year? Yeah, let's do that. Okay. I think Tetris. Probably just Tetris. If we could land Tetris or Super Mario Land. Let's do Tetris. Okay. So size of Tetris ROM. Size of Tetris ROM in Game Boy. So in archive.org, how about whatever? I'm getting distracted. Okay, let's see, what do we have here? What did it generate? Okay, so here's the plan. The CPU is fully implemented with all opcodes and 388 passing tests, but there's no way to load a ROM file. The next step is a cartridge class that can open a GB ROM file, parse its header metadata, and store the raw ROM bytes. Memory integration comes later. This is just the data container and parser. So the files to create, okay, you want init, which is good. We want GB cartridge, that's good. And then we want a test, and then we want empty init for the test. Great. Okay, so cartridge class design, we have a constructor, we have cartridge with the ROM path, opens the file at ROM path, reads all the bytes into memory, and parses the header. That sounds about right. So instance variables, we're going to have entry point, which is going to be probably just an array, a Nintendo logo, another array, and then title, which is going to be a string, and then CGB flag. Okay, that's just going to be a boolean. Probably another number here. Okay, and then another number, maybe a boolean for the destination code. Checksum byte, probably another number, and then number. Okay. Lookup table, fine. Okay. Tells us, okay, so these are going to be enums probably. And then API methods, read at address, take the size and the length of the ROM data, and then validate header checksum. Sure. Okay, so the header checksum validation at 0x014D is computed as, so we just basically go in this range here. We take the ROM address. Okay, so this is just easy math. So we're just gonna go and basically do a bitwise and on 1 byte. And then how we compute the checksum is take the current checksum, subtract it by the value at the specific address in our ROM data, -1, and we just do that within this range of addresses. And then we just check to see if the current checksum that we computed matches that expected as specified by the ROM. Okay, so error handling, file not found, value error. Okay, that's fine. Test is fine. Okay. Yes. Auto accept edits. Okay, so I just predicted those data types. I don't know if that's going to be the case, but yeah, let's auto accept edits. I do not want to clear the context because I think that's useful information to keep consistency. Okay. It's funny because I doing this with Claude allows me to focus more on like specific architectural and implementation details versus like if I were to use local coding, I'm just so obsessed with just making sure like the thing is actually performing correctly, like in terms of speed and accuracy. Here it's like I do have a more trust in the bigger model, and it just allows me to just do more thinking. Okay, so it's creating the cartridge class. Okay, it did that. Let's check it out. So we should have created this folder with cartridge. It didn't even create the cartridge class. Oh, that's the test folder. Right here is what we want to look for. Look at. Okay, so we have cartridge types. So we have, okay, so there's various ones, and I think the Pokemon one is going to be from here to here, as stated, 0x0f, 0 all the way to 0x13. I am guessing Pokemon 0x13. Either that or this one because of the save file. It needs a battery, right? So you have basically the cartridge type is telling us what kind of hardware is inside the cartridge, right? So you'll have a memory bank controller. you'll have a timer, you'll have some cartridge RAM, and then you'll have most likely like a CRC battery, like well, not CRC, like the CR 32 2032 battery, or is it CR 2032 battery? You have one of these things inside. These little cell batteries right here. So I think that's what it's telling us. And then you have RAM sizes. You have either 8 KB, one bank, 32 KB, four banks, 128 and 64. Wow, it's kind of amazing we had cartridges that were that big in terms of RAM. Okay, and then simply enough, just f.read binary to the ROM path. Minimum of 336 bytes is required for the ROM header. So we can parse the header here. We're gonna parse it as raw bytes into here, and then we just basically do some manipulation to get the number. Okay, and then we're going to just remember. So the ROM types here are dictionary, so we can index into that dictionary to get the type name. Sure. And then read bytes. So read 1 byte from ROM data to give analysis. So eventually this read here is going to be integrated with memory. But right now we're just going to assume we're going to just get straight ROM data. And we also have the checksum, and then yeah. Okay, so all green 28 cartridge tests pass. Okay. Now, let me ask this question. Does it make sense to continue to store the header data as raw bytes? Why did you choose this design decision? I'm curious. Why choose the design decision to represent some of that header data as raw bytes? Because if you take a look at it here, or is it right here? Raw bytes. Okay, good question. Let me think about this honestly. For most of the header fields, I didn't store them as raw bytes. Titles decoded string, cartridge type, RAM size are stored as integers. There are derived fields like cartridge type name and ROM size that provide human readable values. Okay, well, fine, fair enough. I just noticed those two things. I should have been more specific. The two fields I kept as raw bytes are entry point and Nintendo logo. Here's my reasoning. Entry point, this is machine code, typically NOP and JP. There's not much value in parsing it further right now. It's 4 bytes of CPU instructions, not really data with a meaningful scalar representation. That's a good point. That said, we could parse into something like no op, true, jump target, blah, but that feels like over engineering since nothing will consume that structure. Nintendo logo, this is 48 bytes of bitmap data that the boot ROM compares byte for byte against an expected pattern. Its only real use is validation. Does this match the expected logo? Storing it as raw bytes is a bit natural fit since there's nothing to decode. So the short answer, I store things as raw bytes only where the data doesn't have a more meaningful representation. Everything that benefits from being parsed, okay, is already parsed into its useful form. Yes, that's good reasoning. Yes, this is good reasoning. Can you actually comment with that justification in the cartridge class itself? It is very useful so that future readers can understand the implementation decision. Okay. Just for my own future self, really. The reason why. Okay. We still need to get the Tetris ROM. How do we do that? Tetris Game Boy ROM download? Does that even... is this the right place? Console ROMs? Game Boy? There's Super Mario Land. How big is that one? Oh, that looks rather large. Yes. Okay, let me just ask Claude. Okay, done. Okay, Now, quick aside, is Tetris a good ROM to load first? I wonder if it is because it seems small, but then there might be quirks to it. Yes, Tetris is a great first round test with. Okay, so reason why Tetris is good because it's ROM only. That's true. I know that for sure. No bank switching. The entire game fits in 32 kilobytes and maths directly. Okay. No cartridge RAM. Simple hardware requirements. Great. Great. Okay, let's do that. Okay, so I downloaded the Tetris Game Boy ROM here, so we can start using that as our test ROM. So okay, let's. So okay, what should I say? Okay, I downloaded a Tetris.gbt here. Tetris.gb. FYI. Okay. Yeah, so let's see if our cartridge class can load it. Pretty sure it can. Okay, so great. So now um we read the title in as Tetris cartridge type 0x00 ROM only. ROM size code is going to be 32 kilobytes. So this is actually coming this is coming off from our cartridge class. So all this information here is tapped from all this stuff here, and that's the header, right? So if we actually did this just to play, here, if name equals main, okay, this is test, right? So cart equals new cartridge, and then we'll just define the ROM path absolute. Copy path. Not new, but yeah. I was thinking of another language earlier. Okay. And then what we can do is we can just take the title. Let's just print the title. Print cart.title. So it's the same thing, right? So let's go to cd source cartridge. Actually, this first, I think source.env. Do we have virtual environment? We do not have a. Is this probably running straight from? It's independent. Okay. We should have had at least a virtual environment, but there's like no dependencies here. Okay, so source cartridge. Then we can just do Python gb cartridge.py, and notice how we were able to output Tetris here. So what it's doing with Cloud is just printing out these instance variable in a nice formatted way. Let's actually do this. Control to toggle. Okay. Can you create a helper to actually print that the header information in a pretty way like you did to test? I like that. Okay. I think next step. Okay, so I think the next step here is probably the memory integration. So looking back at here, this is our integration. And I would even say this, like let's see if we can even, I don't know, is this possible? Let's see. Control V. No, we can't. We can't. Okay. Can we specify file? Oh, we can. Okay. Let's. Oh, whatever. Okay. Let's talk about memory. I was thinking that we should use the same instance of GB memory that the CPU uses. So basically, CPU plus cartridge share memory instance, and then that means cartridge takes in a memory instance in the constructor. What do you think? So right now, if you look at the design, CPU does take in memory in the constructor. So we're gonna probably add a memory here in the constructor. Not sure if, I mean, maybe we can, let's see. I think that's the right direction. There should be one memory instance that everyone shares, but I push back slightly on cartridge being the one that takes a memory instance. Here's my reasoning. The cartridge is a data container. It represents the physical cartridge chip with ROM bytes and header metadata. On real hardware, the cartridge doesn't know about the Game Boy's memory bus. Instead, the memory bus reads from the cartridge when the CPU accesses addresses in the ROM range. So the dependency direction should be CPU takes in memory, memory will receive cartridge. So memory holds a reference to the cartridge. And when get value ADDR is called for these memory addresses, which is going to be mapped to the cartridge ROM, memory delegates to cartridge read address. The cartridge itself stays simple. It doesn't need to know about memory at all. So this also means memory constructor or method like load cartridge takes the cartridge instance. Okay, that makes sense. Okay, let's have a method, not a constructor. Writes to 0x0000, 0x7FFF, and then they're either ignored or routed to the MBC register. And the cartridge class is we just built, doesn't need any change at all. Okay, so the cartridge slot is just a connector that the memory bus reads from. Does that feel right to you, or did you have a different integration in mind? So that's about right now. I think that makes more sense. So basically, well, actually, this dependency is kind of weird anyway. So memory receives that. So then cartridge is then, actually, we did have the right arrows. So, yeah, so then memory will take in cartridge. So like this, inside, I guess. Yeah. There you go. We don't need an arrow. It'll be transparent. So, delete, something like that. Okay. Okay. Then I think load cartridge is a good helper to have. But thinking about it, it might not be needed because we can't really hot swap cartridges anyway. I am debating if we can just put it in constructor since we can't really hot swap cartridges in a Game Boy in real life anyway. Yeah, we can't really do that in real life, so what's the point? Trying to not make sure my head doesn't block anything. So let's do that. Okay. That's a great point, and you're right. On a real Game Boy, you insert the cartridge before powering on. You can't swap it while running. That said, I lean toward keeping both options, except an optional cartridge in the constructor, and have load cartridge as a separate method. Here's why. Testing. Our existing 388 CPU tests all create memory with no cartridge. If we make cartridge required, we'd have to update all of them. With it optional, everything stays backwards compatible. Boot sequence in a real Game Boy, the boot ROM runs first, okay, and then unmaps itself, and then the cartridge ROM becomes visible. If we ever emulate that, we'd want to load the cartridge after the memory is created. The constructor still works for a normal case. When you're just spinning up an emulator to play a game, you pass the cartridge right in. Okay, so then if you think about it, taking into consideration of the boot sequence, it doesn't make sense sense to have the cartridge be received as a dependency by the constructor anyway, with as a dependency into the memory constructor anyway. Maybe we're just good with a single load cartridge method. Yeah, I think if we're taking into consideration we want to emulate a real Game Boy, then if the real Game Boy actually doesn't really take a cartridge immediately, then yeah, maybe we just leave that be and just load the cartridge manually. So the boot round runs first, then the cartridge becomes visible. So the natural flow is create memory, create CPU, then load cartridge into memory when ready. A single load cartridge method is clean, simple, and matches a real hardware sequence. No constructor parameter needed. Want me to go ahead and implement that? Yes. Yeah. Let's do that. And I'm pretty sure Claude is going to try and also implement the memory reads and all that stuff. Okay. So I can see there's a duplicate set value shadowed by line 6787. I'll add load cartridge, wire up get value to delegate to the cartridge for ROM reads, make ROM writes in no op when the cartridge is loaded, and clean up that duplicate. Why not? Okay. Let's just like have it do everything first and then we'll review the code. Yeah. And then I guess there's like reasoning why I would like to, because I think, we have to remember this is ROM. We can't really write to memory. So if we're going to try and write from 0x0000 to 0x07FFF, it should be a no op, given that it is ROM, right? Okay, so all the CPU tests are good. Then cartridge tests are good. We can still load Tetris. So that's good. No regression. Okay, so basically reading this code here, if we take a look at memory, we first create an instance variable with no cartridge. Then we load a cartridge, so we just take an instance of cartridge. And then, let's see here. I would like to just at least give it a type. Cartridge. I don't even know how to spell cartridge, right? So then we can just do from, was it cartridge dot gb cartridge import cartridge. Yeah, there we go. Okay, so we can import that. Then map address is interesting. Actually, there's no change here. Set value. There were two of them. Why were there two of them? Were there two of them? Let's see. Set value, and then we also had set value. That's odd. Probably from DevStroke. Okay, so get value. We want to basically map. So first, and before you want to access RAM memory, if the memory address is less than 0x7FFF, and we do have a cartridge loaded, we want to just basically read from that cartridge address because it's memory mapped. Otherwise, we do normal CPU system memory reads, and then for writing values, we just basically ignore it because it's ROM. We shouldn't be. Okay, that looks easy enough. Cool. Commit and push. Cool. Okay, so now we have that. We have a cartridge loaded. We have it mapped into memory. Now at this point, we need to think about how to get the CPU to start executing with it, right? And this is tricky because how do we like kind of sense that, right? So like what do we use to kind of debug our CPU? Oh, I wanted to type in. That's why. It's okay. We'll leave it be. Okay. Um, maybe it's just my Python skills not that good. Okay, so the question now is like, are we ready to load the ROM and start having the CPU execute stuff, or should we get some ROM test ROMs and run the test ROMs themselves? So um, let's see. Oh yeah, we shouldn't be doing that. Okay. Yeah, we should. By the way, you should not be committing ROM files. Okay. So now what I want to do is I want to instead of like Tetris, which is why I was leading on to this, I want to get some like homebrew Game Boy ROMs, right? So um let me ask. Now let's I need your advice. Now I need your advice. I would like to have some recommendations on some ROMs that are by the community to actually do CPU implementation tests. I think it is better to use that for now rather than Tetris. Yeah. So I wanna basically get those types of ROMs and load them in and then run the CPU. So then like I think usually what ends up happening is that these tests run and then they emit a value into some memory address. We can check that memory address and then see if it's expected result, like unit tests, right? They're like unit tests for the CPU implementation, but like using the real hardware. And now that we have a ROM, our cartridge loaded into memory, we can do those types of things. Maybe I can just look for it too. Game Boy, awesome Game Boy development. So what do we have? Do we have like example ROMs? Custom cartridges. How about test ROMs? Test ROMs. Blarg's test ROMs. Maybe that's helpful. So CPU instructions, maybe it's gonna recommend Blarg. Watch. Okay. Ah, I did. Okay, so CPU instructions has Blarg CPU instructions, the gold standard for CPU testing. Test every CPU instructions individually across 7 subtests. Cool. Yeah, let's just do this first. Okay. So yeah, we have also instruction timing for cycles and then memory timing. And capture serial output writes to that just a few lines in memory. A timer to detect when the test is done. It writes results in loops forever. Okay, yeah, let's do this. Okay, let's hook in support to capture output and then timer first. Then I will download and store the Blarg test ROMs. Okay. So while Claude is doing that, and this is like, I guess, this is how I program with AI. Like the AI become the hands, and then AI, I guess, becomes the real person that does stuff. Okay, so we have uh, instruction timing. So we can just drag that to where uh, desktop. And then we also have CPU instructions. We can drag that to, where did I put it? Desktop. It was in desktop, right? Desktop. Okay, so we have these two. Then we'll have desktop. And then we can just drag that stuff in to ROM. So let's put a subdirectory blarg and then put this stuff in here and there. Then we'll have 2 ROMs. Okay, great. Okay, so we have these two ROMs, and there we go. Okay, so let me explore the current memory implementation and understand how to best add serial and timer support. Okay, whatever. Serial output capture timer. So what do we do? We want for the timer. How thorough should the first implementation be? The Game Boy timer has 4 registers: div, TIMA, TMA, TAC, and ticks based on CPU cycles at configurable frequencies. A full implementation ticks every cycle. A minimal one just handles registers. It doesn't all tick. Let's just do full. Yeah. Yes, let's just do the full timer. I just don't want to do it again. So full timer it is. Let me write the plan. So let's write the full timer, and then we'll read what it is doing later. But basically, it is just using the cycles to kind of make use of time. So I think every cycle. So if we increment the CPU by 4 cycles, this is basically 4 ticks, I think. And we do need to kind of like make sure that those registers automatically update after we run instructions. So I have a feeling that this is way more complicated than I assumed. Is it? Let's see. Whew, okay. Let's do it. So context. We need to run Blarg CPU instructions test rounds, which output results via the Game Boy serial port. Okay, the serial ports at memory address locations. So remember, memory mapped I/O, right? So 0xFF01, 0xFF02. We also need a working timer subsystem, which is in registers or addresses 0xFF04 and 0xFF07. Since Blarg tests and real games rely on timer interrupts, this gets us from CPU that can execute instructions to CPU that can run real test ROMs and report results. So the files to modify, we need to change gbmemory.py to just basically map these memory addresses, okay, on the sets and gets. And then we need to create these files. So it's a serial port handler, captures output from here, these addresses. We need the inits, we need the GB timer, and then we also need serial tests, and timer tests. Okay, so the serial port. How the Game Boy serial works. The Game Boy has a simple serial port with 2 registers. So this is like hardware serial port, and it just sends simple data. So SB, serial transfer data, the byte to send and receive, so like the physical real like value, and then the serial control register. So these 2 memory addresses are kind of like registers. Serial control, bit 7 is to start the transfer, bit 0 is the clock select, internal or external. Blarg test uses serial as a debug output channel. They write a character to SB and then write 0x81 to SC to start the transfer with internal clock, and we capture each byte written this way. Great. So the implementation is pretty simple. It's just to have these 2 registers represented, and then the captured buffer, and then read. Okay, so the address. If it's 0xFF01, we just return this. 0xFF02, we just return this one. And then write, same thing. But then we also need to keep into consideration of the what do you call it, the control bits, right? So if it's 0x81, that's going to be internal clock. So basically, we're going to append the value in self.sb to the output buffer. Then we're going to clear the bit 7 of SC to indicate that the transfer is completed. Okay. And then return the output as ASCII string. Okay, great. Okay, so the key behavior when SC is written with bit 7 set, transfer start, and bit 0 set, internal clock, the byte in SB is transmitted. We capture it in our buffer. This is exactly what Blarg tests do. Okay, So then the timer runs off the CPU clock and has 4 registers. So this is the timer now. So we have 4 of these memory addresses that will we henceforth be referring to as registers. So the divider register is going to be the 8 bits of the 16-bit internal counter that increments every T cycle. So every 4.194 megahertz, right? So every 4,194,000 cycles, writing any value resets to 0. Timer counter increments at a frequency set by TAC. When it overflows, it triggers a timer interrupt and reloads from TMA. TMA is a timer modulo, value loaded into TIMA on overflow. Timer control, bit 2 enable timer, bits 1 to 0, clock select. So the clock select, TAC bits 1 to 0. So we have 0. It's going to be 4 kilohertz. 256 kilohertz, 65 or 64 kilohertz, and 16 kilohertz. Okay, so internal counter, the timer is driven by a single 16-bit internal counter that increments every T cycle. Div is the upper 8 bits of the counter. Okay, so yeah, this actually, okay, so let's ask this. Because the implementation is the same as like the serial. We just need to, it's memory mapped again. And tick is going to be called by the CPU after every instruction to basically increment all and manipulate all our registers here. It's going to be here, right? So it's going to be cycles used. Cycles used. So again, if we run something for 4 cycles, it's basically 4 ticks. So tick self cycles. So what do we do with those cycles? So for every T cycle in cycle, so it's going to be range. Okay, so we're going to increment the internal counter, and then we're going to check for all these things. So the address dispatch, okay, so that's easy, and this is in the memory integration. So again, memory mapped IO, and we'll do the same thing in the timer, and we'll just write the tests. Okay, yes, auto accept edits, and then let's have it go in more detail about the significance of the timer. So when we say auto tick, I think it's just basically whenever you run your CPU, it just handles you, like tick gets called automatically. Okay, so getifying. What are we getifying here? We're going to be getifying the serial port handler. So that should be in the serial folder. Oh, that's yeah, right here, IO. So it's still doing that. So the serial port handler classes are done. It's exactly what we thought. Memory mapped IO here. Just basically if the address is 0xff01, we just return back what the value corresponding to that register is. And then otherwise we just return 255. I think this is just arbitrary. And do the same thing here. Logic. Yeah, that looks right. Here we just turned out buffer into ASCII string. Okay, that's fine. And then in memory, we just basically have the serial port here, load serial, and that's with that chain of hardware initialization that we were talking about with the load cartridge earlier. Then additionally, we have the memory mapped IO, and yeah, we just account for it in serial handler. Where else? Oh, so as far as timer goes, that will be in the CPU because it's CPU related. So the timer, there's an instance of the timer here. We're just going to, okay, so we're gonna just tap into the, wow, okay, so we're just gonna tap into the existing timer in memory. Okay, that's interesting. Let me just ask that later, like why do we need to do it that way? But okay. Then we just call self.timer tick. because I think we're gonna have issues with initialization, right? Like, okay, let's say we initialize. I think the most independent thing would be the memory first, and then we're gonna initialize everything else. Uh, sure. Okay, hold on. Question about initialization of timer in the CPU. Why get attribute? Does this mean that memory has to be instantiated first above all else and then else? How is the instance of timer alive? If we are loading timer lazily after initializing the rest of the hardware. So I'm confused about the order because there's a chance that like the timer doesn't really ever get initialized since it's defaulting to none and it's just using whatever is inside the memory. So okay, so it's kind of realized what it's done, right? So the get attribute line is unnecessarily confusing. Let me trace through what actually happens. The realistic initialization order is mem equals memory, timer equals timer, mem.load timer. Okay, then CPU equals memory. Okay, so the get attribute in the CPU constructor happens to work if the timer was loaded to memory before the CPU is created. That's a fragile assumption about the initialization order. Meanwhile, load timer in memory already handles the other case. Huh. Okay. So I have two paths trying to solve the same problem, neither which is clean. The simplest fix, just initialize self.timer and none in the CPU constructor and let memory load timer set it. That's the single source of truth. The timer gets wired to the CPU when it's loaded into memory regardless of order. The timer gets wired to the CPU when it's loaded in memory. Okay. So this is none, but load the timer after creating the CPU. Okay. The issue is that load timer is called before CPU, so self CPU doesn't exist in memory when the load timer runs. I need to swap the order, create the CPU first, then load the timer. Okay. All 466 tests are fine. Okay. Can you show me now the initialization order? I am still skeptical. I'm skeptical because then there's like a specific ordering here. Okay, so there are two initialization orders. Oh, I guess I was right to be skeptical. It's already changing stuff. So basically, when you're initializing memory, mem CPU is none, mem timer is none. Then when you initialize CPU, sets mem.cpu to CPU, CPU timer to none. Then you create timer. Then you load timer. So mem.timer is a timer. Timer memory equals mem. Has attribute checks passes. Okay. But then this one breaks silently. So you remove the guesswork and have CPU init pull the timer from memory if it's already there and have load timer push to the CPU if it's already there. That way either order works. Okay, that's fine. I'm okay with that. You need to document it though, right? Like, yeah, that stuff you need to document because there's a specific ordering to hardware initialization. Yeah, so this was a real problem. That's why I was skeptical because I was like, this is still not robust. So after it's done compacting, I want to kind of poke at it a little more and go, okay, do you feel like this will cause a lot of circular references? right? Should we just use dependency injection as necessary? Okay, so Claude attempted to fix the initialization order, but I just want to kind of poke a little bit more. It still seems like we're really depending on tribal knowledge to know how to initialize the hardware here. I wonder if this is actually a code smell. Would we act? Would we? Should we consider dependency injection into constructor, or at least, okay, so actually we cannot consider dependency injection to constructor because that doesn't really mirror how the hardware loads. So should we consider writing a main runner, right, to load up the hardware as a startup method or function? Like what I'm trying to say is like this is fragile. This is very fragile. So I think we need to write like some sort of driver, like some sort of Game Boy now, like a Game Boy class, right? So yeah, then there you go, Game Boy class. Okay, load timer, load serial, then load cartridge. Run. No one else knows. Okay. Okay. Yes. Yes. Build it. Then add more comments about the initialization order and why it is important. Okay. So that fixes our issue here because we finally now have a Game Boy class, which it took us this long to get, but that's just on me for not working on this project often enough. It's funny because this is simply just for another bigger project, which I don't think I'm gonna get to anytime soon at this rate. But this is the reason why I'm sitting down here, like trying my best now to like think this through and make sure we get it right the first time. Um, Now, next thing before we want to proceed is I do want like a comprehensive overview of what the timer actually does in the Game Boy so that we can understand that because we understand the CPU very well. We also understand the memory and how memory mapped IO works. The serial ports are pretty straightforward, but the timer is kind of hazy in my head. So I want to at least just kind of go over this exercise and like, what is the timer in Game Boy? Why is it significant? I'm a noob, so please help explain. Um, yeah. Anything else I'm curious about? No. Okay. Okay, cool. Okay, cool. Now I want to understand a bit more about the timer in Game Boy. I am not as familiar of the technical concept and its necessity. Would you mind going over that with me so that I can appreciate your implementation? Uh, yeah. Why is it significant? Why is it significant? And this will help us understand, right? Like this will this will give us a reason to appreciate why the timer is necessary for our Blarg's ROM test. And then after that, I say, hey, the ROMs are in here. Let's do something. Let's run the tests. And I think let's just try to get the tests running for instructions and timing. And then commit everything, update agents.md, and I think we're good for today for our session. And we'll have ROM loading implemented, at least just with the one bank or the 32 kilobyte bank. Anyway, Okay, so let's read this word for word. Okay, great question. Let me break it down from the ground up. What is a timer? At its core, the Game Boy timer is just a hardware clock that counts up and fires an interrupt when it overflows. Think of it like a kitchen timer. You set a starting value, it counts up tick by tick, and when it hits the top 255 to 0, so when it overflows, it dings and fires an interrupt and resets. So it's just like a thing to regularly do interrupts or tell the CPU to address interrupts. So why does a Game Boy need one? The CPU runs instructions as fast as it can, but the games need things to happen at predictable time intervals, not after n instructions, but every x microseconds. The timer gives the software a reliable way to say, wake me up every n microseconds without busy looping. The real use cases: music and sound engines. Pokemon's music plays notes at precise intervals. The timer interrupt fires, the interrupt handler advances to the next note, returns, and the game never has to think about timing music and its main loop. Input polling. Check the joypad at a fixed rate, not whenever we get around to it. That's true. RNG seeking, random number generation. The div register is always counting, so games read it as a source of randomness. It's not random, but it's unpredictable from the player's perspective. Pokemon uses div this way. And Blarg's test ROMs. The tests we're about to run use the timer to detect whether the CPU is executing at the right speed. So how it works mechanically. There's really just one counter under the hood, a 16-bit number that increments every single T cycle, which is basically 4.194 megahertz. Everything else is just different views of that counter. Okay, so div, you just read the upper byte. Since the full counter increments every T cycle, the upper byte effectively increments every 256 T cycles. You can't set div to a value. Writing anything to it resets the entire 16-bit counter to 0. So all of this, games use this as a free running clock they can peek at. TIMA, so this is the real timer. It increments when a specific bit of the internal counter falls from 1 to 0, a falling edge. Which bit? That's chosen by the TAC. Okay, so the TAC is in this configuration. Then the TIMA ticks every number of cycles here. So I would say it's every 16 T cycles is the highest precision, I suppose. Okay, so when TIMA overflows past 0xFFF, it reloads from TMA, so the game controls where counting restarts. It sets IF bit 2, requesting a timer interrupt that the CPU will service. Okay, so TAC is just a control register. The clever part, falling edge detection. This is why I implemented it as a per cycle loop and tick rather than just dividing. The real hardware doesn't count every 1024 cycles. It watches a specific bit on the internal counter and increments TIMA, the instance that the bit transitions from 1 to 0. This matters because writing 0 to div resets the whole counter, which can force the falling edge mid-count and cause an unexpected TIMA increment. Games and test runs rely on this quirk. Great. Okay. So yeah, TLDR, the timer is how Game Boy software schedules work at a fixed real-time intervals without blocking the CPU. One free running counter drives both a general purpose clock divider and configurable interrupt source. It's small, 4 registers, 50 lines of logic, but without it, games can't play music on time, test ROMs can't validate CPU speed, nothing happens at the right pace. Okay, cool. Cool. Can you actually put a summary of this great explanation in at design.md? Okay. I thought that was very good. So now let's just point it to the ROMs and see what happens. Okay. Yeah, let it go for a minute or so. We're almost there. Cool. Alrighty. So now we have all this useful information. I think it's just really good information to learn. In case if we ever want to do this again in another language. I starting to think that Python was a bad choice, but it's okay. I think it's fast enough with our system. Okay, everything's still passing. 479 tests. Cool. Okay, now I put the ROMs in. Where was it? Blarg. Uh, in ROM. Uh-oh. I think I know what happened. Because it's ignored now. In ROM slash blarg in the project. Should be 2.gb files. Okay, so yeah, we have the CPU instructions, MBC1. Okay. A couple of things to note. CPU instructions is 64 kilobytes. Has 2 ROM banks, which means it uses MBC1. Our cartridge class currently just does flat self-ROM address reads, which only works for the first 32 kilobytes. For 64 KB ROM bank 1 is the default mapping, so it might work without explicit bank switching, but if the test writes to the MBC1 bank select register, we'll need to handle that. Instruction timing GB, okay, 32 kilobytes fits in the single ROM bank. Even though it's marked MBC1, it won't need bank switching. This one should work as is. Want to try running instruction timing first since it's simpler, no banking needed to see what serial output we get. That'll tell us immediately if the CPU is executing correctly or where it's failing. Yeah. Let's do instruction timing.gb first. Can you also write a script for this? So we can consistently run it in the future. Okay. Yeah. So I think probably the next thing we need to do is implement bank switching. So I mean, given the fact that this thing can churn out code like no other, it might just be worth to just implement like all of them. So yeah. So run blargpy instruction timing GB. No serial output. The ROM is executing but not producing any output yet. This could be a few things. Let me check what's happening at the entry point to see if we're actually running the ROM's code properly. Okay, so we're supposed to jump. Yeah, so we're supposed to jump to 0x213. The ROM copies itself from 0x4000 to WRAM and then runs from there. Let me trace where the execution ends up to understand why there's no output. Still in the copy loop, copying 4 kilobytes from ROM to WRAM. That takes 130k cycles. Let me give it more. Oh geez, that means Python is pretty slow for this. Uh-oh. Uh-oh. Am I using a lot of CPU? Yes, I am. So PC is at 0xC3C3, executing JPC3CG in an infinite loop. It's stuck. 0x02 means it's enabled the LCD stat interrupt, but we don't have a PPU generating those. Let me trace more carefully to see what goes wrong after a copy. It's already stuck at 140k cycles. Let me catch it earlier, right after the copy finishes and jumps to 0xC0000. Okay, so we definitely have a CPU bug. If the ROM is getting stuck at 140k cycles in, then we need to find out where in that instruction, like right before then, right? So that's why it's going right after the copy finishes, because there's most likely a jump that happens to 0xC000. Yeah, it's hard to tell too because 140k cycles, you have to like kind of reverse engineer that and then figure out how many what instruction corresponded to what based off of the number of cycles running. but that's okay. I think Cloud handles can handle it. When I wrote my Nintendo emulator like years ago, I had to do this by hand too. Like I had to like debug and print out like memory addresses and keep count of like what cycles and what happened right before then, and then just try to play guesswork to kind of figure out what was going on. So yeah. Anyway, the copy is broken. WRAM is filled with 0xC3. The first ROM byte repeated 4096 times. The LDAHL plus instruction isn't either incrementing HL or what? Or isn't reading from the updated address. Let me check the handler. The handler looks correct. Let me check how set register works. Maybe 16-bit register write is broken. Okay, let me check for cartridge read. Maybe the 0x4000 plus range reads are wrong. Nope, that looks fine. Address is still the full address, and the ROM data is 32 kilobytes, so index 0x4000. Okay. So we're doing everything right. Maybe our jump is wrong. Like our initial jump, right? For our ROM. Either that or the copy is good, but the jump again is wrong. We'll see. Wow, it's actually really just yeah. Okay, it's really just like going line instruction for instruction. Okay, so find the bug, look at line 92. Sure. We're gonna go from what? What's FBPC? Oh, 20 FB is gonna be at this location here. So we're gonna jump, not 0, -5. So if it's non-zero, we're gonna jump, right? We're gonna jump. So we jump to 0x205 instead of 0x206. Then at 0x205, it executes byte 0x10 stop, which skips this at 0x206 entirely. Okay. So the JRNZ -5 displacement is 0xFB, which is basically -5 signed. From PC, after reading a 2-byte JR instruction, the target should be 0x020B plus -5 or 0x0206, but it's landing at 0x205. Our JR handler is computing the right jump target off by 1, which is using PC before advancing the past operand byte or something similar. Let me check. Found it! The JR handlers all compute PC -1 plus offset, but PC has already been advanced past both the opcode and the operand byte. So the correct formula is just PC plus offset and not the taken path incorrectly backed up by PC. Cool, thanks for the fix. Okay, now we're going to... Okay, so we have all 5 JR handlers with the same bug. Then that means we have to fix all the tests. That's what I'm saying, like, tests only pass. Really, it's based on how you interpreted and understood the code, right? So, technically the tests were wrong. So it wouldn't really be helping us anyway. That's, I guess, the weakness of not understanding specific implementations or designs. Okay, so yeah, this is gonna fail. Okay, for all the JR tests. That's fine. We can just adjust. So yeah. So all tests are passing. Now it's wanting to run everything again. Hopefully we... Oh, wait, that's cool. Blark's instruction timing test passed. Every instruction cycle count is correct. The JR off by 1 was a sneaky bug. The test had the same wrong assumptions baked in, so it went undetected until we ran the real ROM code. This is exactly why Blark tests are the gold standard. Yes, let's commit and fix and talk about how we can get CPU instructions GB working. Great, so we know that our CPU isn't actually a disaster. We know that it works, so a combination of what? Qwen, GPT OSS 120B, Claude, like all these models just working on the CPU, we know it works now. Okay, yeah, so let's focus on the instructions themselves, that's more complicated because you need memory bank switching. Okay. Um, how do we do this? Again, I seriously think that we should just go on ahead and implement the entire thing. But yeah, so it's trying to do it right now. So it's yeah, it's oh, I guess it's just trying to run and see what happens. Um, I guess so. Whatever. So the reason why I'm happy that the timing instructions passed is because we were keeping track of cycles, and I was just so scared that the opcodes JSON file with those cycles, right? Like this JSON that contains all those necessary cycles was wrong. But of course not, right? This is like gold standard JSON. But I was scared that we were like digging into the wrong thing, especially since I was barely like validating whether or not these models were actually picking off the right values. So yeah, that was just my concern. So yeah, we're failing. You know, I'm not surprised that's failing because it's not a 32 kilobyte ROM. It's 64 kilobyte ROM. I think at some point Claude should just give up and accept the fact that maybe it's not. Okay, yeah, then you know, how about we just implement MBC right now? How many MBC do we need? 5? Okay, well, okay, hold on. Good data. Here's a clear pattern. Every fourth test fails with error code 05 and the rest pass. There are two things we need to address to get this working. We need MBC1 bank switching. Okay, no, no duh. Okay, so right now, okay, whatever. Repeating 05 error. The fact that every fourth test with the same error suggests a systematic issue. Probably set up a init check that each subtest runs first. It could be related to banking. Oh, yeah, okay. Yeah, MBC 1, 2, 3 right now. Or in actually, let's see. Oh, before we do that and implement MBC1, I would like you to give me a thorough explanation on how MBC switch or bank switching works with cartridges. Yeah. Let's figure out how this works first, so then we can let it cook in our head, and then when it implements it, we can kind of review the code properly because we know how it works, right? Okay, so here's the explanation. It's a lot, but okay. Let's do it. Great question. Let me explain this from the ground up. The problem, not enough address space. The Game Boy CPU has a 16-bit address bus, so it can only address 64 kilobytes total. But that 64 kilobytes has to hold everything. The ROM, the RAM, the VRAM, the I.O. registers, and the stack. The actual space reserved for cartridge RAM is just only these 32 kilobytes. So that's 32 kilobytes of ROM address space. Pokemon Red, for example, is 1 megabyte. So how does a 1 megabyte game fit through a 32 kilobyte window? The answer, bank switching. The cartridge hardware sits between the CPU and the ROM chip. It contains a small controller chip, the MBC, memory bank controller. So let me see if I can get a picture of that. Game Boy MBC. It's probably one of these two. So yeah, it's one of those two. So you have a bunch of chips in here, right? And one of them is going to be um the MBC. So it's a physical thing, okay? Um and acts as a multiplexer. So it's a device that just like flips things back and forth. The MBC maps a portion of the full ROM on into the CPU's address bank, sorry, ROM bank 1 window. Think of it like a filing cabinet. The ROM chip is the full cabinet with 64 drawers for a 1 megabyte ROM. So basically 1 megabyte divided by 16 kilobytes. The CPU can only see through one drawer size slot at a time. The MBC is a mechanism that slides the cabinet so a different drawer lines up with the slot. So ROM chip has bank 0, bank 1, bank 2, bank 3, all the way to bank 63. So basically bank 0 is always visible. Bank 1 is visible when the bank register specifies B1, visible at this memory location when bank register specifies 2. CPU's view, okay, so CPU's view is always going to be limited to this range here. So how the CPU tells the MBC which bank to use. So here's the clever part. The MBC has no dedicated I/O port or control register in the CPU's address space. Instead, the game writes to the ROM address range, which is normally read-only. The MBC intercepts these writes. Okay, so it's a controller, right? Since it sits between the CPU and the ROM chip and interprets them as commands. So the game will actually write to a specific special range. The NPCs can see this and go, whoop, that's for me, right? And based off of that value, right, it's going to do a few things. So if you write to address 0 to 1 FFFF, it disables external RAM. So write to 0x0, write the value 0x0a to enable. And then if you write anywhere from address 0x2000 to 0x3FFFF, select ROM bank number. 0x4000, 0x5FFF, select RAM bank or upper ROM bank bits. And then 6000 to 7FFF, select banking mode. So, okay, sure. So when a game wants to switch to bank A or bank 5, it does this: load 5 into the A register and then basically load the value of A into address 0x2000, which is right here. So ROM bank number. The CPU thinks it's writing to ROM, which normally would do nothing, but the MBC chip intercepts the write before it reaches the ROM, reads the value, and reconfigures its internal bank pointer. The next time the CPU reads from 0x4000 to 0x7FFFF, the MBC routes it to a different section of the physical ROM chip. MBC1 specific. Bank 0 is always at this address. We know that. This is fixed. The game's entry point, interrupt vectors, and common routines all live here because they always need to be accessible. Bank 0 cannot be selected at 0x4000 to 0x7FFFF. If you write 0 to the bank register, MBC1 treats it as 0x1. If you write 0... Oh, okay, so yeah, so this, you can never, ever load the 0th bank into here. Okay, so if you try to do that, it'll just kind of rewrite it to 1. This is a hardware quirk. Bank 0 is already visible in this range, so mapping it again at this second bank would be pointless and would make bank 1 inaccessible. So the 5-bit bank register. The write to this range only uses the lower 5 bits of the value, giving a range of 0 to 31 for ROMs larger than 512 kilobytes, 32 banks. The upper bits come from 4000 to the 5 FFFF registers, okay? The ROM offset calculation. When CPU reads address, add ADDR in the range of this range, so the first bank, 0th first bank. Physical offset is going to be the selected bank. So is it the 3rd bank, 4th bank, 32nd bank times 4000 plus address minus 4000? Wait, what? If we're at the third bank, let's just say that, multiply that plus the offset. Oh, okay, yeah. So the current address that we want to read minus 4,000, that gives us the offset plus the where we start at. So this calculates where we start at, the base address, and this is going to be the offset. So then now we get the real byte here from the physical. Okay, so we have bank 3 times 4,000 plus ADDR minus 4,000. That will read at anywhere from here to here in the real ROM memory. Is it? Let's see, ROM data. That's true. The physical ROM memory. Okay. Yeah, that's really confusing. So basically, um, ADDR is going to be used, like we're going to get value at ADDR. Internally inside ADDR, it's going to be intercepted by cartridge. Cartridge is going to do this calculation and give us back the real data here. Okay, so what CPU instructions GB is doing, the ROM has its common code in bank 0 and its 11 individual subtests spread across banks 1 to 3. When it wants to run subtest N, it writes the appropriate bank number to the MBC and then calls into 4000 where the subtest code now appears. When subtest finishes, it returns and the main code can switch to the next bank for the next subtest. Without bank switching, every read from 0x4000 to 7FFF returns bank 1 data. Subtests in banks 2 and 3 never get executed. Instead, the CPU runs bank 1 code again, or garbage, which is likely why we see the repeating error problem. Okay, so MBC is what we'll eventually need for Pokemon, so this is just basically it, right? It works almost identically to MBC1 for ROM banking. The main additions are real-time clock and slightly different register layout, so getting MBC right now directly prepares us for MBC3. Okay, fine. For this, we need a track selector bank register in the cartridge class, default 1. Intercept writes, okay. Well, let me ask you this. Why such a large memory range for MBC interception if we only care about a few bytes? Example, 0x2000 to 0x3FFF is quite large. That's my curiosity. Why such a long range? It's probably just me not knowing anything. Okay, so because it's not memory map registers, it's hardware signal decoding on the cartridge PCB. The MBC chip is a physical chip sitting on a cartridge circuit board. It watches the CPU address bus and data bus. When the CPU performs a write, the MBC looks at the address lines to decide what to do, but it doesn't check all 16 address bits. It only looks at a few of the upper bits to determine the region. Okay. Oh, I see. 3 wires. That's the reason why. Okay, that's it. 3 wires. MBC doesn't care about bits 0 to 12 at all. Writing all the other stuff will just do the same thing. The chip was designed to be cheap. Okay, fine, fair. Okay, let's just implement MBC1. Try to keep implementation simple and write the necessary tests. Go for it. Okay. Yeah, let's just do that, and then when the time comes, we'll just put more effort into the other MBCs. We just want to see if this actually works. Here it goes. Okay, so chibi cartridge.py is going to have in an MBC. So we're gonna first have an instance variable. I think we're just gonna initialize it right then and there with 1, sure. RAM bank 0, RAM enabled false, banking mode 0, so that's ROM mode. And then number of ROM banks is going to be self ROM size divided by this many because that's the amount of regions, but by default it's going to be 2. Now for read, well, if it's MBC, right? RAM, so the offset is going to be, so this is going to be if it's less than 0 or greater than this. RAM index out range, we've always had that, I think. No, we didn't. That's new. Anyway, address less than 3 FFFF. We're gonna just return the ROM address. No need for offset. That's a 0th bank. Now, if we have a higher offset, we need to go to the ROM bank, multiply that by 0x4000, get the offset here, and return the right bytes. Then we just do the opposite for the was it the read, except this one has to do with the MBC, like the regions of memory that we were just asking about, right? So that table with RAM enabled, ROM bank select. So this will change the ROM bank. Okay. Okay, so that's if the game starts writing at these values. And at some point, we had to modify memory to account for that, right? So self.cartridge. Okay. And then it's already running the CPU instructions, but this looks okay, I guess. We have errors. Wonder why. So when we write, or actually, let's take a look at read, right? So if we're trying to read at specific cartridge value, for example, cartridge read address, then we really have to be aware of the specific bank that we're using, and that's the reason why we have right here. So then ROM bank switching happens on that write. So whenever we want to flip the banks, that's why we have to write the specific address, and the game will actually do that, I think. Okay, so the output completely changed. We see 11 distinct subtests instead of repeating pattern. Bank switching was a structural issue. Let me give it more cycles to finish test 11. Okay. So that's good. $500 million cycles. If we're running 4 million, if we're running 4 million a second, and it's taking us this long to run, does that mean that our CPU is slow? Whatever. Let's just figure it out later. I'm just happy that this actually works now. Yeah. So if this works, we can just commit and push, but it looks like not. It looks like we're still getting what? Let's see. Okay, so 4 results are in. 7 of the 11 tests pass, 4 fail. So the good news, MBC1 bank switching worked. The JR fix we did earlier is confirmed. Test 7 passes. Interrupts pass, and most instruction categories are solid. The 4 failures likely indicate specific instruction bugs. Error code 05 on test 1 points to specific assertion on DAA, CPL, SCF, and CCF special ops. Error code 01, tests 5, 8, and 9 mean that the first assertion failed on each of the test suites. These are specific instruction bugs we can hunt down. Want me to start investigating, or would you like to commit, and tackle? Yeah, commit first, and then fix all the instruction bugs. Yeah, let's just do that. I think I can just let it run too. As far as like, do I care? No, most likely not. It's like this is most likely due to our like kind of mishaps on open code, vibe, all that stuff might have just compounded to these weird bugs. Although I do remember that SCF and CCF were actually pretty simple, so it's kind of concerning. We'll see. We'll just let it run and give us a summary of what was wrong. Okay. Yeah, this is a run, and I'll say, hey, give me a summary of what was wrong for each instruction once it figures all of it out. I only have 8% context left before it starts to auto-compact again. Whoa. Could not read from remote repository. Why is that? I guess that was just like a one-off. I have no idea. But yeah, let's just have it do its thing, and we'll come back later. Okay. So Claude finished debugging and fixing a bunch of bugs. Um, Actually, it caused its own bugs, and then it ended up fixing it. So, uh, not many things were that wrong. I believe it was just. Well, you know what? Let's do this. Right here. So, basically, the first bug it found was the add HL. The H flag was wrong. Okay, so the problem is that this is always false. An 11-bit mask value can never exceed 0x7ff. Basically, just looks like you just. Oh, okay, so you just add to. You just mask the 11 bits. Was that 11 bits? Or 12 bits. Sorry, you mask 12 bits, then you add 12 bits again, and you see if that actually overflows. Okay. Um, the next one is pop AF, the lower 4 bits. I'm guessing since we store all 16 bits in AF, the Game Boy's F register lower 4 bits are always 0, so we just blindly stored it. We had to mask. Okay, and SBC flag. H flag was hard coded to false, but when carry is set, okay, so A should be true. Sure, cool. So yeah, okay, let's do this. Run both blarg tests now. Both blarg tests now to really make sure we are good. Okay, so let's run both, but I'm happy because now we know that our CPU is working fine. Instructions are good. Timing is good, and we fixed a couple bugs. Yeah, so this looks like that the timing worked. No, instruction timings worked. And then we also will have the CPU instructions technically working, just to make sure that it's not exit code 1, which means error. And then we'll have a commit, update, design MD, agents.md as necessary. And I think next time, let's actually get. Actually, let's have it. Let's ask Claude what else is left, and then we can go from there. So this one's going to take a while because there's a lot of instructions to execute. Okay, so both are passing. Awesome. Okay. Awesome. Looks like we have a working CPU. Yay. Okay. What I want to do next is commit and push. Then commit and push. Wait. What I want to do next is for you to update design.md, agents.md, then commit and push. Okay, so now it's going to come back, compact, and we'll just wait a little longer again. Great, looks like it's updating things just fine. Update phase 6 to completed and add notes about the bugs that were fixed. Technically, yeah, we did do phase 6, huh? Let's see. Yeah, phase 6, real ROM integration testing. Okay, cool. So now we're going to commit and push. And then let's just, for next time, let's actually discuss ideas of where to go next. Okay, looks like we have CPU implemented. Let's stop for now, but before we do that, let's plan out the next thing, or let's decide on the next thing to implement. I was thinking of going with video. Yeah, because we do video, we can also work on joypad. Once we work on like the controller, and once we work on the controller, we can go back and do like MBC2, 3, and then we can just like loop back and do some sound, maybe. Let's see. Video is the natural next step. It's the biggest remaining subsystem, but also the most rewarding since you'll go from serial port text to actually seeing the game render. Here's a quick lay of the land for the Game Boy PPU. What it does, renders 160 by 144 pixels, one scan line at a time, 154 scan lines per frame, 144 visible, 10 V-blank, tile-based, 8 by 8 pixel tile stored in VRAM. Okay, 3 layers. So we have background, window, and sprites. VRAM, okay, we know that. We all know this. And then the PPU registers, so specific memory locations to actually write control data to. Mode state machine, okay. What makes it complex? Mode timing must be cycle accurate. Okay, but we've already kind of verified cycling is fine. Yeah, so okay, DMA transfer, sure. Anyway, what Pokemon Red Blue specifically needs: background plus window rendering, sprites, scroll registers, no Super Game Boy Color yet, just 4 shades of gray initially. A reasonable build order would be PPU register plus mode state machine, text alongside CPU, background rendering, window rendering, sprite rendering, stat interrupts, VRAM, OAM access restrictions, and DMA transfer. Yeah, let's do this on the next session. Update agents.md, commit and push again. Yeah, let's do that next time. Yes, thank you everyone. Long session today, but I think it was very productive.